Hi again. Today is interesting topic. Green's function. So we study the equation Laplacian u equals f. Here u of x, no x, x1, xn in Rn, but we usually don't solve this equation in the whole space. Much more interesting and deeper theory is if we are in a bounded domain D. No, it can be a ball, a cube, whatever, but it should be bounded. And the boundary of D, let me denote it by Greek letter gamma. And not only we solve this equation, but even from our experience with the ordinary equation and with the previous, we considered the string equation. Equation requires some initial or boundary conditions. Here we should have boundary condition. And we usually consider two sorts of boundary conditions. Either u on the boundary equals some given function g. It is called Differential. Problem, or we can solve again delta u equals f in d u du dn on gamma equals, say, h, given function. This is called Neumann problem. So we solve either this or this. No, in fact, there exist a lot more problems, but no, we have to start from something. So let's begin with these problems. I don't specify much about what is the regularity of functions f and g. We consider classical solutions, so so u should be at least twice differentiable so that we could substitute it into Laplacian operator, and f should be, we can also consider it differentiable, but in fact we don't need to differentiate it. G should be once differentiable, but we'll see. We'll see. And our main tool in studying this equation, it is surprisingly powerful tool, is the Green's equality. So suppose, say, u of x, v of x are twice differentiable functions in domain D. D bar means that they are continuous and the derivatives are continuous up to including the boundary. Then this Green's equality is the following: integral over D u times Laplacian v dx equals integral over d v dot Laplacian u dx plus integral over gamma u dv dn, n is the external normal to the boundary, minus v du dn ds. So this is the Green's equality. Now in particular, consider example. V equals 1. What we'll get here? So integral over d u 1 times Laplacian u times Laplacian of 1 dx equals integral over d 1 times Laplacian u dx plus integral over gamma u times d of 1 dn minus 1 times du dn ds. Laplacian of 1 is constant, so Laplacian 1 is 0. Derivative of 1 in the direction of n is also 0 because 1 is constant. So these two terms go, and what we have? We have integral Laplacian u dx over d equals integral over gamma du dn ds. Yeah, it is already a powerful equality. Now let us go further. We have already defined, but I will remind you, the notion of fundamental solution. What is this? It is a function phi of x, in fact phi of module x, yes, x and the whole space Rn, such that Laplacian of this function equals delta function of x. Now, I explained what this means. We can somehow a little bit modify this function, approximated by a smooth function. And this function, phi, if you substitute into Laplacian, gives us 0 everywhere, but some small spot near 0. And the integral of Laplacian is 1. Yes, and it depends on parameter epsilon. When epsilon goes to 0, this spot is of size epsilon, so a spot somehow tends to just 1 point, 0, the origin, and the integral of Laplacian keeps to be 1, so it is a true, the limit is true delta function. And we have the formula for this. Phi of r equals 1 over 2 pi logarithm r if n equal 2. And here we have, let me write in the following form, 1 if 2 minus n omega n r 2 minus n. So what is omega n? Omega n, it is the n minus 1 dimensional area of the sphere of radius 1 in Rn. Yeah, so we have a unit sphere, and its n minus 1 dimensional area, which is called here ds, integral of ds over this area, is denoted by omega n. Now, in analysis, in integral calculus, we found this value of omega n for all n. I would say that omega 3 equals 4 pi. Yeah. It is the usual area of a ball of radius 1. We don't need much more. I think let us stay in space of dimension 2 or 3. I think it's enough. Okay. Now let us write the Green's formula, use Green's formula for some function u of x. U of x, no, at least C2 of d. D is domain in Rn. So u of x, let me write the following chain of equalities. Equals integral over d u of y delta of x minus y dy. I think you have one moment. Okay. Now let us look. Laplacian of function phi of x is delta of x. Now, if you consider Laplacian of phi of x minus y, it is delta at the point y. Yes? So, it is equal to integral integral over d u of y, Laplacian of the function k of xy dy. What is k? Laplacian with respect to y. K of xy equals phi of module x minus y. So it is the same function, but for any x, if we consider it as a function of y, it has a singularity when y equals x. Yes, because it is model, let me write, it is 1 n minus 2 omega n module x minus y to the power 2 minus n. So when x goes to y, this goes to infinity. Now let us apply the Green's identity. It is integral over d delta u of y, k of delta, yes, with respect to y, k of xy dy plus integral over gamma u of y dk of xy. Here x is just parameter, it does not change. So x is parameter, only y is variable of integration. D n at the point y minus k of xy d u d n y, du of y, ds also at the point y. Yeah. So this is the formula, and now let us look at this formula. We are solving one of functions. So let me remind you that Laplacian u is denoted by f. U on gamma is g. du dn on gamma equals h. Yes? It is my notations. So it is equal integral over d f of y k of xy dy plus integral over gamma u of y, not gamma, it is g small of y dk of xy d and y minus k of xy h of y all this dsy. So in this formula, you see, we started from u of x. Yes? So it appears that here is solution of our problem. Solution. If you know u, Laplacian u, which is f in the domain D, if you know G on the boundary, the values of U on the boundary, if you know the normal derivative on the boundary, then this formula gives the answer, because we have here all ingredients. Unfortunately, it does not work. It does not work because here it is implied that we consider the following problem. We consider the following problem. Delta U equals F, U on the boundary equals G, du dn on the boundary equals H. All this. And it turns out that this problem usually has no solution. So if you substitute here if you substitute the function f, g, h in this formula, the result will be negative. I mean, what we get will not satisfy the boundary condition, because this term will change the boundary, the normal derivative on the boundary. This term will spoil the value of the function on the boundary, and so this this formula, it is true. So how does it read? It reads as follows: if u, Laplacian u is f, if u on the boundary is g, and if du dn on the boundary is h, then this relation holds, that u at every point is given by this formula. But it does not read in other side, in other direction, that if you write this formula, you miraculously have solution. It does not work, and the solution is still far away from us. But let us consider some particular case. Suppose we have the following thing. We have just delta u equals 0. Suppose that Laplacian u is 0. So what happens? This is harmonic function. It has some values. Delta u is 0. It has some value on the boundary, and its normal derivative has some value on the boundary. So if you substitute it in this formula, then f is 0, so this term goes, and you have u of x equals integral along gamma g of y k dk xy dny minus k of xy h of y dsy. So we have this formula. This formula also does not say much, because if you have just g, then you are able to find unique solution of the unique u such as this Laplacian u is 0 and on the boundary u equals g, and h will be found afterward. We cannot say that h is arbitrary function, as h is uniquely defined by g in this setup. But we have one immediate corollary, immediate consequence of this formula. Let us look at the function k of xy. K of xy equals phi of module x minus y, where phi was written here. Phi is either logarithm of x minus y, or it is some power of x minus y with some coefficient. So if here it is d, it is gamma. At last I can draw it. It is the point x inside, and here integration goes along gamma. So this point, variable point of gamma is y. It is outside. It is on the boundary. And what we have for every y, we have g of y is for a fixed y is a number, and here there is a function of x with parameter y, and the k is a smooth function. K is a smooth function outside of x equal y, and here x is inside and y is on the boundary. So here k of xy is a smooth function, and if you take its derivative along the unit normal at this point and at the point y, unit external normal, then it, as a function of x, it will remain smooth function. And the same with this h of or du dy is some number for a fixed y, and as a function of x, it is also a smooth function. Yeah. So we have for any y, this is a smooth function, and we have a family of smooth function depending on y on the boundary. We integrate it, and as a result we have that the harmonic function is smooth. What does it mean smooth? It means that it has all derivatives of all orders. Yeah. So the conclusion from this function that u of x is class C infinity. So any solution of Laplacian equation, if it has at least some reasonable regularity, say C2 regularity, it has just two derivatives. After that, we see automatically that it has all derivatives of all orders, all continuous derivatives of all orders. Yes, it is, if you recall what happened with the string equation, the situation was the opposite. This equation has a lot of solutions, weak solutions, which have not enough derivatives. It can have even no derivatives at all, just continuous. Can have even jumps in some sense, yes? Or if it may be a function of C2, but no more, not more regular, yes? And here we see a new phenomenon, that this function is, if only it satisfies the Laplacian equation, it is infinitely smooth. Moreover, this function is analytic. No, you did not study mostly analytic functions of several variables. It's a real analytic function. I mean that it can be expanded near every point in a convergent Taylor series. which no converges in some inside some ball. Yes, so this function is truly very nice. This function, but it does not permit us to solve the problem because if you consider, say, the Dirichlet problem, this formula does not permit us. We have to somehow improve it. And here comes what is called Green's function. Green's function. It is the following function. So consider first the function k of xy. K of xy is good. As it gives us a solution, but it does not permit us to satisfy the boundary conditions. At least we don't see how to do it. So let us a little bit correct it. G of xy equals, it is Green's function, k of xy, the fundamental solution, minus function, say, w of xy. And this w has the following, is the following. For any x, w xy, delta with respect to y is 0 in D. And G, say, k of xy plus, minus w of xy equal 0 when y is on gamma. Yes, this means that w of xy on gamma equals minus k of xy, I would say y on gamma when y on gamma. So x is inside, y is on gamma, and so g of xy g of xy equal 0 if x in D, y in on gamma. Yes, and Laplacian with respect to y g of xy is 0. In D. So to do it, we have to find this correcting function. Now, this means that we have to solve another Dirichlet problem. The Laplacian y is 0 and y on the boundary, no, x is parameter, y on the boundary is a given function. Yeah, so it is not easier than initial problem, but it is good. So if you find this function, then you are done, because now let us write the following. First of all, Laplacian with respect to y g of xy equals Laplacian with respect to y k of xy minus Laplacian with respect to y w of xy. W was harmonic function without any singularity, so this is 0. So it is equal Laplacian k of xy, which is delta of x minus y. So it is just delta at the point x. And then we can write the similar identity, again use the Green's identity, and find the following, find solution of the Dirichlet problem. So we write so our problem, delta u equals f in D, u on gamma equals g. It is the Dirichlet problem. So u of x, suppose u is solution. U of x equals integral over d u of y delta x minus y dy equals integral over d u of y Laplacian with respect to y g this time of xy dy equals integral over d. Now we move Laplacian to u by the Green's formula. Laplacian u of y, g of xy dy plus integral over s u of y d g of xy d and y minus d u d and y g xy dsy. What can you do it? Equals, let me write it here. It's continuation from here. Equals, again, integral over d. Laplacian u is f of y g xy, and here we see u of y plus integral over s u of y dg dny, and here g xy is 0 when y on the boundary. Yes, we are on the boundary. So this term is 0. I don't write it. U of y on the boundary, I'm sorry, it is g small of y. Yes, by this. So now we have excellent formula. If only we had the Green's function, then we have both components of this formula, and the Dirichlet problem is solved. Yes? No. But here are two obstacles. One is very big, other is also big, but not so big. First thing, why are we sure that this solution, this problem has a solution at all? Not every problem has solution. So this problem may have no solution. So it should be proved somehow that this problem always has solution. Or at least say what are conditions, necessary and sufficient conditions for this problem to have solution. It is not obvious that this problem is always solved. That is one thing. And other thing is how can you construct this Green's function? Or equivalently this corrector W, corrector function, to make Green's function from fundamental solution. It is more or less equivalent thing. All these problems are pumped one into another. And now I wanted to show one example when this works and gives a very good result already. Before we go into this theory and start proving existence and some other general things, let us extract some the first corollary of this. First of all, if delta U equals 0, we are solving this equation, that's f equals 0, then the solution is even simpler. U of x equals integral over gamma, the boundary, g of y dg xy dny ds y. Yes? So this is our formula. And let us look again at this formula. Let us look at this formula. Consider, so suppose we have a harmonic function in some larger domain. And consider the situation when our domain is a ball around the point x, so x is the center, with radius say r. So d is a ball of radius of the point center of the point x and radius r. And this space is coordinates x, y1, y2, and so on, yn. And delta u of y is 0. So we have the function which is harmonic inside in this ball of radius r. And let us write down. So first of all, in this case, we can write down this solution. U of x equals so x is a fixed point, yes? So what is g of xy? Of xy. Note that if x is not the center, then it is a non-trivial problem. But if x is in the center, it is the following. It is phi of module x minus y and it is enough to add some constant, namely minus phi of r, simply so. Yes, phi of r is a constant. And then, just for this point x, which is at the center, you have that this is g of xy. We found it for just one x. Yes, and it again it alone gives us an interesting thing. So dg of xy d and y. So what it is? If x is here and x is fixed, just y, it is the radial function depending on the distance from the 0 equals simply dr. Yes, the function. One moment. G of xy, which is equals some constant 1 divided by 2 minus n omega n r 2 minus n minus constant phi of r. Yes? So d g dn, so we take here and go along this unit normal, is just derivative of this function with respect to r. So dg d and y equals 1 over 2 minus n omega n times 2 minus n r to the power 2 minus 1 minus n. Yes? And this constant disappears when we differentiate. Equals 1 over omega n r 1 minus n. Now, dg d and y on the gamma. A gamma is this. Gamma is a sphere at the point center at the point x and radius r. Equals 1 over omega n r to the power 1 minus n. And then let us look what is here. U of x equals integral over the sphere, the point center x and radius r, u of y, no, I write u of y, times dg d and y times 1 over omega n r to the power 1 minus n dsy equals 1 over omega n r n minus 1 integral over s of x r u of y dy. And now let us look, what is this? This integral over the sphere of the function, our function, and this in the denominator is the area of s xr. Yes, it is the area, omega n is the area of a sphere with unit radius, and this is area of the sphere of radius r, whatever it is, large or small. Yes, so what is written here is nothing but, so we take integral of the function over some domain and then divide it by the area of this domain. In this case, domain is the sphere. Yeah? So it is the mean value of average of the function of u of y. So u of x equals integral over sphere of x of radius r, u of y dsy divided by the area of s xr. Yes? Equals mean value of u of y on the sphere S of xr, center of x. So, and this relation is called the mean value theorem. So we proved mean value theorem. And this theorem is, no, we'll see how it works further, this theorem alone. But next, what we are doing next, we have to extract some other implications of this theorem. Then we will find the Green's function in some simple domains. I mean, simple domain is half space, yes? So in the whole space we have fundamental solution which works, but it requires some justification that it works. I will show some next time. Half space, it is not bounded but already domain, not the whole space. Then a ball. We found Green's function just for one point, for the center of the ball. Yes, but it's interesting to find it for all the points of the ball. And then I will try to prove the existence of solution of the Dirichlet problem. Yes, in fact, Dirichlet problem and Neumann problem are considered in parallel, and much is done for both this and that. No, I will consider just Dirichlet problem. So it is principally important problem how to prove existence of solution of this problem. It is highly non-trivial thing and one of the central achievements of analysis in 19th century, so it requires some attention. Let's finish for now. Have a good time. Bye.